We're going to do one thing before we get into quantum mechanics, and that is finishing up a relativistic calculation. And that is the actual calculation for kinetic energy. In class, I showed this page. And voila, here's our result. Kinetic energy final minus kinetic energy initial. Well, we're in calculus class. This is one of those cases where it looks like it must be simple, but I'm going to go out on record as saying not really that simple. So how do we do this? First, we start with the definition that work is integral of force dot distance. Right? The laws of physics have to be the same whether we're talking about relativistic or non-relativistic situations. And so applying Newton's second law, the net force, if we're just talking about the force, we're trying to find, well, it's the net force, so it's the net work, so it's going to be the net force. I just should have put net there and didn't. So net force is the derivative of momentum with respect to time. So this is just substitution in the first line, just nothing but substitution. Now we start to get tricky. First, we have dpx dot dx. So the derivative in momentum with respect to time dotted to dx. Funny thing about derivatives is I can move the dt. I have two d's. I have dx and dp. I can just move that dt over. So this equation I end with here is identical to this one here in meaning. But I move the dt from, instead of being under the dp, to being under the dx. Why do I do that? Well, dx dt is something simple. What's dx dt? Velocity. Because it's a vector position, it's velocity. And so now I have dp dv. If we were doing classical physics, classical P is equal to mv. So dp dot dv would just be equal to mdv, or excuse me, it was not dotted to mdv dot v, right? And then we would say, well, dv and v are going to be in the same, same direction. And that would just be, when you integrate it, integral of v dv is 1/2 v squared. So that'd be 1/2 mv squared. That's how you classically get your kinetic energy. And of course, you'd have plus c if I have no limits, right? Plus c because there's an offset. Well, I'm doing this relativistically. So momentum is equal to gamma mv. So the integral of dp dot v is the integral of d gamma mv dot v. Now, once again, with the dot product, I can drop off the vectors because their v is in the same direction as v. And m is a constant, so I'm bringing it outside of the integral. The derivative gamma v, v. Now, you're probably thinking, at least it'd be wise to think, that's crazy, that's weird, right? Because I have d of gamma v, not just d of v. How do I analyze this? Well, the way I did it before class seems to be the way I should go. It seemed long, but I can't think of a better way. If you come up with a better way, like midway through, you say, wait, you could have done this quicker this way. Don't feel bashful. Go ahead and say, call me out. But what I did is I said, well, let's use the product rule with gamma and v. So So there's using the product rule, right? Now I'm going to use the chain rule on the first one. Now I at least have them both in terms of the same thing, both in terms of dv. Does that feel like we've gotten very far? Yeah, probably not. We've got that derivative in there.
No, you explain chain rule.
The chain rule?
Yeah,
Okay.
I'm not very familiar with that.
Change color to something I haven't used. So just chain rule. What you've done is you've effectively multiplied by 1. Using things the way I did before, I'll show it as there I've multiplied it by 1, right? Multiplied by dx, which by definition is 1. And then I just move the dx over. That's the way that I did it here. The purpose of the chain rule is I have a function and I want to take derivative of that function with respect to a variable, but the function is dependent on another variable that depends on the third one. That is, I have, let's say, a function of x, but x is a constant times time. And so if I have a function with respect to x, I can say, well, the derivative of the function with respect to time is the derivative of the function with respect to x times the derivative of x with respect to time. So it's a way of allowing me to shift the variable of the derivative. And so that's what I had to do here because I had d gamma, which was not the variable I wanted for my derivative. I wanted dv. So coming back to what we have now, we have v d gamma dv plus gamma. And so now I'm going to take gamma and find the derivative of gamma. The derivative of gamma with respect to v, what is this? Doing the derivative. I'm going to rewrite this just to make it simpler. There's another way of writing gamma to make life easier.
So it'll be -1/2 parentheses stuff to -3/2 times -2v over c squared.
Right. You had, and we could have done this using the chain rule if we wanted to. We could have said, let u equal 1v squared over c squared. And so gamma is equal to u to the -1/2. So d gamma du is equal to -1/2 u to the -3/2, but then I have to do the chain rule. Yeah. And so that is what we did. It's just you did it without saying the words chain rule, but it's how you did it. Now, if we combine this all together, we note that this minus sign and this minus sign will give us a plus, and the 2's cancel. And so this is equal. And what is this thing right here?
Square root cube all over. I mean, all under 1.
It's this thing here, cubed. And so I can shorten my writing by saying this is equal to v over c squared gamma cubed. So that means this here is equal to v times v over c squared gamma cubed plus gamma dv. And of course, v times v over c squared, yeah, I just can.
Isn't the dv on the outside of the parentheses?
Yes, it is. Thank you. Well, what can I do with this? I'm going to come back up and put it all together then. So I have, well, actually, continue with this. What do you suppose that thing in parentheses is? Or not parentheses, brackets. It turns out it simplifies. One over gamma squared is going to be 1 over 1 minus.
You mean just gamma squared, not 1 over gamma squared.
Or yes, gamma squared. Yes, I do. Thank you. Now what would you do if you're trying to simplify this thing?
Common denominator.
Okay, get a common denominator. What I'm going to do is make this v squared over c squared minus v squared. Right, so I distributed the c squared into the denominator, the first one, and then 1 will become, for common denominator, but then if you look at that, v squared plus c squared minus v squared, the v squared subtracted out. But that thing in the brackets is gamma squared. So this is just equal to gamma cubed dv. So now, did I draw up something? So all of this was just looking at that part. So now I can rewrite my, or gamma cubed dv is what I had for this. And I put the v in the middle there. I could have put it in any order. So I need to find that integral of gamma cubed v dv. So that's getting to this line here. You see that it took a lot of work to go from here to the next line. For the non-calculus class, we just say, and so it is, because they don't know calculus. But it should be unfulfilling to simply be told, and so it is, right? How do you know it is? You're just taking it on faith. Well, we don't like to take a lot of things on faith. We do like to take on faith that God exists. Did you, Alex?
I haven't been studying because I assumed you left it open for the student projects, but like I haven't left it open.
Maybe it's Dr. Seth is leaving it open.
Maybe he's leaving it open for the students project.
Yeah, it could be. Okay, there's one last thing here then. Integrating that thing. Aren't you glad you know calculus? Let me back up on that statement. You should be glad you know calculus because you can actually make sense of these things. If you don't know calculus, it doesn't make sense. It's just like, well, I guess so. And I guess so doesn't make me very happy. I want to know why. So continuing on then, we now need to evaluate this integral. I am going to now expand gamma so that I have m integral of v dv over 1 minus v squared over c squared to the 3/2 power. How do you, my good friends, integrate this baby? Let u equal. Excellent. Good work, gentlemen. When I first did it, I just said v squared over c squared. And then after I was halfway through, I was like, well, that was a stupid choice of mine. You made the correct choice. You know, what difference does it make to have the 1 in there? It makes no difference as far as this level, but when I do the integral, it makes a big difference. So du is equal to minus 2v over c squared dv. Therefore, v dv is equal to minus c squared over 2 du. And so I'm going to substitute in this and this to make my integral. There's my minus c squared over 2. Or if you prefer, that's the easy way of writing it for doing the integration. So what do I get when I integrate this beast?
Is that what it is?
The exponent is minus 3 over 2, yes.
You subtract one.
Integrate, you add 1. I'm going to write it this way. What Alex said is correct, but I wrote it this way to make sure we're clear why he said negative 2, divided by the new exponent. And then I'll put plus c because I'm doing it without limits. To me, it's weird to do it without limits. To you guys, I know it's, well, isn't that the standard way? It is in calculus class, not so much in actual application in physics. Okay, so now that we have this, the minus here and the minus there are going to make it positive. This divided by 1/2 and divided by 2 are going to cancel each other out, as it is easier to see the way Alex said it. And so we have this is equal to mc squared over square root of u plus a constant. But going back to u, 1 over square root of u was gamma. So what we have here is calculation, the change in kinetic energy is 1/2 m, or one, it's not 1/2, it's mc squared gamma squared plus, mc squared gamma plus a constant. Well, that constant is going to be whatever we need, and we generally set that constant to, when we're doing the actual kinetic energy, we set it to 0, because why do we want to have an offset? And we have the kinetic energy is gamma mc squared. So there we have the actual calculation. Now, if you look back at my definition here, I actually did it with limits. I did it with limits just so I could say the difference in kinetic energy is final minus initial. Here I did it without limits, just saying kinetic energy plus constant. So what we have there is the actual math showing that this equation for kinetic energy is legitimately derived using the exact same rules as we have used in the past. Exact same rules as classical physics, except for the classical physics problem was completed in that much space. Whereas the relativistic one required quite a bit more space, quite a bit more work. It's more complicated physics. Questions about that?
So basically, whenever we're calculating kinetic energy of something relativistically, we just calculate the gamma before and after, and
that's pretty much it, yeah. Right, that's where the rubber meets the road. That calculation is simple. The derivation that we did, not as simple. Right, so if you have blind faith, relativistic can be simple, except for, you have simple rules. I have to identify what the rest frame is, what reference frame is going to give me the proper time, what reference frame is going to give me the proper length. And then I'll just calculate gamma, do my length contraction or time dilation, addition of velocities equation. Those are all fairly simple things. You just have to think through those things. So if you try to do a relativistic problem and you don't think about which reference frame is going to give me the proper time or the proper length, you're likely to make a mistake. But otherwise, the math that you're going to do is not that hard, but the underlying ideas are much more complicated. Now, quantum mechanics. This and next week, I will review for the exam. Do we have an exam next week? No, I don't think so. I think this week and next week I'll be doing quantum mechanics. And we'll be doing just this one problem, basically, for the quantum mechanics. Yeah, I don't think it could be next week. It's too recent. I haven't even graded the last exam yet. You had an exam a week ago today. Yeah. It's, okay. Although, yeah. So, quantum physics. Now I'm going to give a little introduction here to quantum physics, so I don't have any slides for the introduction. The development of quantum physics itself is, I think, important to understanding what quantum physics is. So, the development of quantum physics starts with what we learned in class yesterday and what we're going to study in the lab today. That is the photoelectric effect and the testing of the idea that you have only certain quantized, in this case, quantized energies for light. That light can have an energy of 1 times HF or 2 times HF or 3 times HF, but no other values. That's a quantum idea. We also have as an outcome of that light behaves both as a wave and as a particle. And so Louis de Broglie, or as we usually say in English, de Broglie, because we don't speak French. His name is de Broglie. That's a G. Louis de Broglie said, hey, wait. If light has both a wave nature and a particle nature, and we're going to say that light is both a wave and a particle, because that's the outcome that we're getting to in this chapter. The light will be a wave and light will be a particle. Then shouldn't it be that other things that are particles can be treated as a wave? And so he came up with an equation for the wavelength of a particle. And that equation was the wavelength is equal to Planck's constant divided by the momentum. So he said we should be able to treat any particle as a wave. Erwin Schrödinger read this, gave a talk about it, and after giving the talk, I can't remember who it was, but somebody said, oh yeah, if that's so, then, what he says, we should be able to treat particles as waves. And the person said, well, if that's so, shouldn't there be a wave equation to describe the particle? Wave equations we've seen, well, we probably didn't see the first one now that I think about it, we didn't have time, but we saw the wave equation from Clerk Maxwell's work. The wave equation is an equation that relates some derivatives, and said if the function fits this equation, then it supports a wave. And Schrödinger, instead of taking that as a setback, said, yeah, probably should. And so he went off and did some work, and he used an energy balance equation, that is, the kinetic energy plus the potential energy is equal to the total energy, and came up with a wave equation, and that is Schrödinger's wave equation. That is the equation that has, on the left side, is total energy. IH bar. What is H bar? I just said H bar. You look up there, you see H with a line through the H. That's H bar. And H bar is Planck's constant H divided by 2 pi. So it's something that we use incredibly often in quantum physics. Sometimes there's a slant on that bar, sometimes there's not. My quantum physics teacher in college called it H slant. He obviously put the slanted bar on it. So IH bar, what kind of derivative are you seeing there? By the curve D means partial derivative. So partial derivative of psi. That trident-looking thing is a capital Greek psi. And what is psi then? Well, psi must be the wave function. When we talked about electromagnetic wave, we had a function for the wave that was something like, let's say, electric field peak times sine parentheses kx minus omega t. That was our wave function. That described all the information you need to have about that wave. It describes everything about the wave. This psi here is going to describe everything about the wave for a particle. Now, going to the next one, the minus h bar squared over 2m times the second derivative. That is what we call an operator for momentum squared over 2m. Operators are functions that act on a function. And so over here we have the energy operator. And this here is the potential energy operator, which is boring. Now, as you could guess, there is a lot more to this than I'm going to possibly tell you about today and a week from today. But this is the basis of quantum physics from Schrödinger's standpoint. You have this wave equation, and you solve the wave equation to find the function that matches it. And once you find that function, it will carry all of the information about your particle, just like when I talked about electromagnetic wave, the wave function for that electromagnetic wave carried all the information about my light. Now that's one of the 2 developments for quantum mechanics. How nice is that to have 2 developments? The second development comes from Erwin Heisenberg. Heisenberg was studying electrons in atoms. And one of the things that frustrated scientists incredibly was not being able to determine what path the electrons are taking as they're orbiting the nucleus. Now, when I was in high school, I thought that they knew this, right? I didn't know physics at all in high school, right? And I thought, well, the electron's doing a circle. Or if it's in a p orbital, given my naivete, what did I probably say if it's in the p orbital? Doing a figure eight is what I said if it's in a p orbital. Those are incorrect answers. It's what I thought were the correct answers when I was in high school. I was very confused. So Heisenberg was frustrated with this. We can't tell what the path is. We don't know much about the electron at all. And he just decided, forget all this stuff. Let's focus on what we can know. And so the things we can know, we call the observables. And we can measure the angular momentum of the electron. We can measure the position, within a large degree of uncertainty often, of the electron. And we can measure the energy of the electron. That's something we can measure fairly readily. And he said, okay, so we have these values. And then he started trying to analyze those values and organize them. And so he didn't know really what he was doing mathematically. He just knew he was trying to find some order in these numbers. And so he took it to another scientist who sent it off to another one. And the one he sent it to said, whoa, you're just doing linear algebra here. This is easy. And so he shows them what they're doing with linear algebra. And that's the other approach to quantum mechanics. There's a linear algebra and a differential equations approach. Differential equations is using the Schrodinger equation. Linear algebra is focusing on just doing these are the observable values and organizing. They give you equivalent results. Now, before I go into it, there's one more thing I have to say. In everything I've laid out, what is there that I've said that's giving you a reason to believe that quantum physics is correct physics?
Wait, one more time?
In everything that I've laid out here about quantum physics, what have I given you that would lead you to believe that it's correct physics, that it's based on sound theory?
Yesterday in class, you said it has never been proven wrong.
That was actually something different I was talking about, but it's still a useful comment. Because that's pretty much where we are with this as well. The quantum mechanics gives us correct answers. In many ways, you can almost think of it like a little black box. You put in a question that gives you a right answer. You don't know what's going on inside that box. We don't have a theoretical basis to say this is what's happening. What we have is, if light has both the wave and particle nature, we don't understand why, then shouldn't other particles have a wave and particle nature? In the origins class, we just had a logic lecture yesterday. There's really no connection between the photon and the other particles that says the other particles have to obey the same rules as the photons. So it's not like we have a good foundation for this, but it's developed and it gives us right answers. There's some real difficulties in quantum mechanics. Things like quantum mechanics is calculating the statistics, the probabilities of outcomes. And Einstein is very famous for saying, I don't believe that God plays dice with the universe. Let's break that down to say what it means, and then we'll figure out how it applies to this. So I don't believe that God plays dice with the universe. What does that mean?
No inherent random chance. Everything follows a set path. It can look random from a distance. So.
Yeah. That nature itself is not random. Nature itself is deterministic. If A, then B. No, if A, then maybe B or maybe C. And basically, his feeling was if we understood it correctly, there would be no fuzziness. We would know exactly what's going to happen. And so it must be a lack of our knowledge that leads to the statistical or probabilistic outcome of quantum mechanics. Now, it's also important to point out when he says God, Einstein's beliefs about God are somewhat variable depending on who asked him and when they asked him. But I think at best you would say he was agnostic. Didn't know that there was God. Was not a person who believed in an active God. So when he's saying God, what he really means is that the laws of physics, that nature is not random. So Einstein believed that there must be more to this. The state-of-the-art understanding of quantum mechanics is right now, no, we don't think so. We think this is the fundamental nature, that nature really is statistical. There's, it's not a deterministic exact system. So there's our background for quantum mechanics. Any comments before we actually try to do a problem? We're just going to do a problem to see how the quantum physics works out. And we'll do the problem between today and a week from today. So any questions or comments before we get into it? All right, then let's get into it. So this equation here has two variables, time and position. One of the first things that we do in quantum mechanics is say, let's try to separate the time variation from the position variation, if we can. And using mathematical trickery, we can do that. We assign psi is the product of two functions. So that's a capital psi, the one that looks like the trident that's vertical, and the one that's tilted is a lowercase psi. Tricky enough, it took me a long time to realize the textbooks were doing that. When I was in college, all the way through, I never figured that out. So capital psi is a function of both position and time. Lowercase psi is only a function of position. And we're saying, let's see if it works out to say that our wave function, which is a function of position and time, can be separated into a function of position multiplied by a function of time. So we're going to test that. We're going to try and see if it works. And when you put it into the Schrodinger equation, when you put it into this equation up here, if the potential energy is only a function of, well, I better put x in this case since I have x. If it's only a function of position and not a function of time, then it turns out that you will be able to write it this way, that you'll be able to have it separable. And when you have it separable, you end up with two equations. There's one equation, and then the other equation is skipping the middle part. I'll just write it over here. There's the other equation. And so this one here only has time as a variable. This one here only has position as a variable. Now, we do a little bit more mathematical trickery so that we have these written with the lowercase psi and no phi, no function of time in it. This one's written with the phi, no function of position. Now, of these two equations, one of them you can solve. One of them, I doubt you can unless you've completed differential equations. Which one can you solve of those two? The bottom one. How would you solve it? This is something we've been doing since we started first semester. How do you solve that? Separate variables, and then you integrate independently. And so if we separate variables, d phi over phi is equal to E dt over I h bar. Well, 1 over I is minus I. Integrate the left-hand side, and you get natural log of phi. Integrate the right side. You have that. And so finally, if I want phi by itself, I have to use the inverse of natural log. What's the inverse of natural log? exponential. And so I have phi is equal to e to the minus. Yes, you're right. I forgot the I. I said move it to the top. I put the minus sign and forgot to write the I.
More mathematical magic.
Yes, that's why you're not supposed to take things on faith. We can make mistakes. And that's a good sign, at least. So there is our time domain solution. That was quick and easy. And in quantum physics, we split that out and we hardly ever look at it. We say we've got that part. Let's not worry about that part. Let's worry about the spatial domain solution. So here's the time-dependent solution. What's the difference? Here I have used Euler's relation. Y'all know Euler's relation? Nope. I have it written somewhere coming up, but I'll write it right here. Euler's relation is that e to the I phi is equal to cosine of phi plus I sine of phi. That relates to other things like definitions of sine. How many definitions of sine do you know? Okay, if it's a right triangle, then sine of an angle is equal opposite of her hypotenuse. You also may know the law of sines, not actually a definition, but another relation.
Identity.
There is an infinite series that can define it, or you can put cosine of phi is equal to e to the I phi plus e to the minus I phi over 2, and sine of phi is equal to e to the I phi minus e to the minus I phi over 2i. Phi is just some random variable in this case. Maybe I shouldn't have used phi because phi means something else in everything else I've done. Okay, you're right. I was like, yeah, that's a good one. A. Okay.
A is usually a constant. We use alpha.
Until you're done.
They look exactly the same anyway. I mean,
No, they don't. Even with my handwriting, they don't.
They look essentially the same.
Okay, but this is Euler's relation, and if you use Euler's relation in these two definitions, you'll see, oh yes, they are indeed the same. So this here is, notice negative sign here, no negative signs here. Because cosine of minus a is equal to cosine of plus a. And sine of minus a is equal to minus sine of plus a. And so those signs were brought out front to give you the minus sign here. So there's our time-dependent solution that, like I said, we almost always ignore it because we know it, we have it, and what's interesting is the spatial relationship. For the spatial relationship, we're going to find what we call stationary states. These are stationary states that we find independent of time and that obey this Schrodinger equation. So for next class period, I'm only going to set this up. I don't have time to actually start, so I'm just going to set it up. We're going to look at a problem where we have an infinite well, an infinite energy well. This is like saying that I have a particle, and if it's inside the well, it has a potential energy of 0. No potential energy. But it's going to take an infinite amount of potential energy to be outside the well. So in reality, that means if we're talking a physical well, the well has walls that are infinitely tall on either side. What's the chance of the particle getting out of the well?
It's infinitely tall.
Yeah. 0, right? No chance of getting out of the well. Quantum mechanically, we're going to have the same thing. If it's infinitely tall, there's no chance of getting out. Now, one of the interesting things in quantum mechanics is if the well has a height of 10 feet, and the particle has enough energy to jump up 5 feet, what are the chances of it getting out?
50-50.
Not 50-50, but not
Yeah, it's
identically zero either.
But it's not high. It's not high.
It doesn't have enough energy to get out, right?
Yeah.
But it
It's
can
not
still get out.
Yeah.
And we call that process quantum tunneling. And so that's one of the crazy things about quantum mechanics. It says that you can have something leave even if it doesn't have enough energy to leave.
Now, what happens to the energy states of everything around it? They just act like it's never there. Energy.
Well, obviously I don't have time to do this problem, so let's just think about that. In this problem, we have this, infinite well. So no probability of being outside. And we're going to work with it next class period. This is effectively the same idea as having a metal wire. A metal wire, the electrons can be anywhere in the wire, no potential energy variation. But they can't leave the wire because potential energy goes really high if they leave. It's not infinite. That not infinite is important because if I bring that wire close to another conducting thing, there's electron could be on this wire, or it could be on this conducting thing. And when you look at its probability of getting out, the probability of getting out drops off as you go away. So if there's nothing nearby, it's eventually coming back into the well. Even if it had enough to have it's outside a little bit, it's going to come back in because it can't get away. But if you have something else that can get away, we call that tunneling because it didn't have enough energy to get over the barrier, but it's allowed on the other side of the barrier.
As long as it goes to another place that has a.
That's right. As long as it goes to another place where it's okay, it can get across a not allowed barrier.
So, but for conservation of energy, that would require that there is no instant where it's technically outside of the well.
Yes. And so that's why we call it tunneling. We say, imagine that you're a prisoner and there's this wall. You could be outside of the wall or you could be inside the wall, but you can't jump over that wall. And so what are you going to do? You're going to dig under it.
Prison break.
Yeah. You're going to dig under it or tunnel under it. And so that's where we get the term tunneling. You're not going to the unallowed state. You're taking a pathway that's not supposed to exist to go from an allowed place to another allowed place.
I think I've asked this before, not in class, so is time quantized?
Is time quantized? I don't even understand why it was such a big deal. But about 14 years ago or so, somebody wrote a paper that said that there is no such thing as an instant time, that is, time is not quantized. And that had, in quantum physics sense, you can see why it would make a difference, being discrete or not discrete.
Tunneling really easily. It's the same thing like when you have an electron going from one energy state to another, it can't exist really between the two, right? So it kind of jumps. But
Yeah.
If there were quantized time, then if it jumped from one quantum time unit to another, then at no point is there time that exists where it is outside of the well.
Well, one thing I'm going to show you is, I'm going to show you, I may or may not, is that, the disallowed place where it doesn't have enough energy for, we can calculate the probability of measuring it there. So that would say, if the probability is not zero, it could be there, even though it doesn't have the energy.
Which means it doesn't require quantized time.
On the other hand, we'll be able to find places in this, places where it's not allowed for the particle to be. Places where there is 0% chance of any measurement ever finding it there. So we will continue on. We just did a little setup here. Obviously, we're like 3 slides into quantum mechanics. Next class period, next Tuesday, we'll continue and actually